Hi, my name is Ali Zaidi, and I'll be discussing Loopapalooza, our compiler-driven framework for investigating the limits of loop-level parallelism. This work was undertaken at ARM Research in Cambridge and the UK, with support from our collaborators at the University of Manchester. Single-thread performance scaling is likely to stagnate in the near future. This can be attributed to two key issues, the complexity wall and the ILP wall. The complexity wall notes that building ever more aggressive out-of-order processors results in a quadratic growth in complexity, area, and energy costs, while the ILP wall notes that there is a fundamental limit to how much ILP may be extracted from a single thread. Speculative multithreading is a possible solution that attempts to find parallelism beyond the ILP wall by executing future instructions in separate speculative threads. While this approach has demonstrated substantial speedup potential, it often achieves these gains at a substantial efficiency penalty. The practical challenges of designing an efficient, scalable, speculative multithreading system requires an in-depth understanding of the various inter-thread dependencies and ordering constraints, which are the key limitations for speculative multithreading performance scaling. The essence of speculative multithreading is identifying control quasi-independent regions from a sequential execution stream that may be executed concurrently as separate threads. This exposes an orthogonal layer of thread-level parallelism across these regions, in addition to any instruction-level parallelism within each region, thus allowing us to overcome the ILP wall. Of course, any inter-region dependencies must be respected, such as any true dependencies through registers or memory. There may also be a requirement to preserve the sequential observable semantics of the original code, requiring each region to commit its results in program order, even though they may execute out of order. These dependencies and ordering constraints must be handled efficiently within any speculative multithreading system. We categorize all possible such dependencies and ordering constraints as either true, false, or structural dependencies. True dependencies may be either static, known at compile time, or dynamic, manifesting at runtime. We further categorize these into frequently or infrequently occurring dependencies. Frequent dependencies include register loop carry dependencies such as induction variables, reductions, or memory accesses that touch the same address across iterations. Some frequent true dependencies are easy to parallelize, such as induction variables, which can be rewritten as a function of the iteration count, or reductions, which can be implemented off the loop critical path via linear or logarithmic accumulation. Of the remaining frequent LCDs, some may be amenable to value prediction, thus becoming infrequent hazards only when mispredicted. Infrequent dependencies can be handled simply by re-executing the speculative thread on a hazard, as their rarity allows us to simply bear this occasional cost. The remaining frequent dependencies, however, require an explicit inter-iteration synchronization to preserve correct ordering while retaining more conservative pipeline parallelism. Structural hazards, such as the stack pointer and stack frame, require support for somehow simulating a parallel stack. While false hazards don't affect program correctness, they are important to the program's sequential observable semantics and thus would need to be preserved in most conventional execution environments by ensuring in-order commit. Given this understanding of the various loop carry dependencies and the ordering constraints, our analysis focuses on three distinct parallel execution models. The dual model is the most restrictive as it does not permit any dynamic dependencies. It can only support manageable static dependencies such as induction variables and reductions, but cannot handle any other frequent or infrequent register or memory dependencies. Dual can, however, support stack parallelization. Next is the partial dual model, which relaxes the dual model's constraints on infrequent register and memory dependencies. This model implements a transactional execution-like scheme where each iteration maintains a read and a write set, and if a read set conflict is detected against a predecessor iteration, the younger iteration must restart. It supports predictable register dependencies in the same way. A misprediction leads to a restart for the iteration with a correct value. However, as we assume that such restarts will be expensive operations, the partial dual model should only be employed when the rate of such dependence hazards is expected to be low. But for our limit study, we assume that these restarts have zero cost and maintain a maximum permissible conflict rate threshold of 80%. If the conflict rate rises above 80%, the loop is marked as sequential in our cost models. Next, the Helix model is a generalized form of DOACROSS and is able to support all frequent dependencies through explicit inter-iteration synchronization. Note that the MIT Swarm architecture, together with their T4 compiler, provides a highly refined version of partial dual parallelization, and as such it performs poorly in the presence of frequent loop carry dependencies that the Helix model can support. We assume all of our execution models can handle false hazards and preserve sequential observable semantics by employing lazy versioning of speculative state. Lazy versioning implies that all writes are written to speculative buffers until the thread retires successfully and its writes can be committed to main memory. Lazy versioning unfortunately can incur this overhead unnecessarily when conflict rates are low, but has the advantage of preserving sequential semantics as all writes appear in program order as the thread commits. An alternative approach would be eager versioning, as is employed by the MIT Swarm architecture. Here, writes are written to main memory directly, while each thread maintains an undo log in case it needs to revert the changes it makes. Committing a thread is a simple process of freeing the undo log, as all writes are already in main memory. This is beneficial when threads are infrequently restarted, as should be the case with the Swarm's partial dual approach. However, all writes are visible across the system out of program order in such a scheme. But this can be fine if one is targeting an unconventional, explicitly tasked parallel execution architecture like the Swarm. We also assume that all of our execution models are able to parallelize the stack when needed, either by simulating a parallel stack through the thread local speculative stores, or via an explicit cactus stack. The Loopapalooza infrastructure takes these dependence categorizations into account and implements compiler passes to categorize loops based on their static dependencies. For instance, only loops containing computable register dependencies may be suitable for dual parallelization. Then, Loopapalooza instrumentation passes add callbacks to our runtime instrumentation library. These callbacks mark each basic block entry, each loop entry and exit, iterations start and end, each function call and continuation, each non-computable register dependence, as well as all load and store addresses within instrumented loops. At runtime, these callbacks are used to track the progression of sequential execution and through the maintenance of internal timestamps, the simulation of any of our parallel execution models. The load and store callbacks maintain read and write sets for every iteration, while the register LCD callbacks can simulate various value prediction schemes. As an example, this figure illustrates how the timestamp mechanisms can be used to simulate the execution time for a partial dual loop execution. All non-conflicting iterations are marked as starting concurrently with the loop start timestamp. If a conflict is observed, such as that between iterations 0 and 2, the iteration start timestamp for iteration 2 and all subsequent iterations is adjusted to the end of iteration 0 in order to simulate a zero-cost restart of the conflicting iteration once the hazard is resolved. A similar thing happens when iteration 5 has a conflict with iteration 2. For the dual scheme, if any conflict is observed, only the sequential loop cost is recorded. The Helix model is simulated slightly differently. All loop iterations start at the loop start time, and the load store callbacks record the maximum conflict timestamp delta between any two accesses across the entire loop. This max delta is then used to compute the conservative synchronization cost that must be incurred as a pipelining delay between any two neighboring loop iterations. To test the relative importance of the various dependence types, we simulate our three execution models with support for multiple combinations of the dependence categories that each can support. We're able to simulate all three models with and without support for accelerating reductions, value prediction, or stack parallelization. Value prediction utilizes realistic predictors. We simulate 4 different predictors such as last value, stride, 2 delta stride, and finite context method. We implemented a confidence-based predictor selection scheme, but found that it had a marginal effect on our results. So instead, we went with perfect hybridization for this limit study, meaning that if any of our predictors is correct, we mark the prediction as correct. Stack parallelization is applied to support loops containing function calls. We assume we have access to either a proper cactus stack implementation, or that we are able to simulate a parallel stack frame by maintaining copies of the stack pointer and stack frame in each thread's local speculative state. We support parallelization across calls to any local functions that have been instrumented by Loopapalooza, as well as any thread-safe, reentrant, or side effect-free library calls. For the Helix model, we simulate support for non-computable register dependencies by lowering them to memory. This is a matter of convenience, as we can use our load store conflict tracking infrastructure to track the conflict deltas for these dependencies as well. We also have support for a few unrealistic settings like perfect value prediction and perfect function parallelization for the do-all configurations in order to evaluate how important register dependencies and function calls are to overall achievable speedups. Perfect value prediction assumes all frequent register LCDs are perfectly predicted, while perfect function parallelization assumes all function calls within loops can be safely parallelized. For our limit study, we assume unlimited resources and support for nested parallelism, so that inner and outer loops can be simultaneously parallelized. Starting with the dual scheme, however, we find that non-numeric benchmarks like SpecINT2000 and 2006 exhibit poor speedups, even with unlimited resources. Due to the restrictiveness of the dual scheme, no combination of settings provided any improvements. The baseline partial dual scheme achieves similar performance to the dual scheme, indicating that infrequent memory dependencies weren't yet the primary bottleneck for these non-numeric codes. Results start to improve when we enable value prediction to convert some of the frequent register dependencies into infrequent ones. The next gain in performance comes when stack parallelization is enabled, indicating that the frequent presence of function calls in key loops. Pushing value prediction and function call parallelization to the limit, however, still exhibits an underwhelming performance improvement. SpecINT2000 only achieves 2x, and SpecINT2006 rises to only 2.6x under these unrealistic assumptions. This indicates that the bottleneck now lies with frequent memory dependencies. The next realistic limit configuration is the Helix model with stack parallelization. With Helix's support for frequent memory dependencies, we see a slight improvement in both suites. However, when we also enable Helix synchronization for frequent, unpredictable register dependencies, we see that both suites see substantial increases in achievable speedup, with SpecINT2000 achieving 4.5x and SpecINT2006 achieving more than 7x in the limit. The numeric benchmarks follow a similar pattern to the non-numeric ones in some respects. In both cases, partial dual benefits from value prediction and stack parallelization, and then Helix support for frequent dependencies further improves the limit speedups. However, the magnitude of the gain is amplified by the numeric benchmarks, as they can be seen achieving 20 to 50x speedups in the limit in the full Helix configuration. Furthermore, the numeric benchmarks benefit far more from the perfect value prediction configurations than the non-numeric ones, indicating that these benchmarks are less constrained by frequent memory dependencies and more by frequent register dependencies. Another noticeable difference between the non-numeric and numeric benchmark suites is that reduction acceleration has a greater impact on the latter each time it is added to an experimental configuration. From the results in the previous slides, we see that the full Helix configurations are able to provide the best performance uplift. While expensive techniques such as value prediction and reduction acceleration provided some gains, these were far overshadowed by techniques that emphasized fast synchronization between threads to support pipeline parallelism in the presence of frequent dependencies. Additionally, the pursuit of ever more sophisticated value prediction schemes is not particularly relevant to the field of speculative multithreading if Helix-style dependence synchronization can be supported, especially for non-numeric benchmarks. Additionally, we observe that parallelizing the stack, for instance by maintaining stack frames in partial dual-style speculative state, is a worthy investment as well. The key reason for the speedup potential of the Helix approach is that it is able to cater to nearly all categories of loop carry dependencies. This means that nearly all loops can be parallelized using this approach, and this results in very high coverage. Recall from Amdahl's law that speedup is not only a function of the parallel resources available, but also the fraction of code that can be parallelized. One interesting point of note is that for any loops that are amenable to parallelization through both the Helix and partial dual approaches, it is likely that the latter would provide a higher speedup as it need not conservatively implement worst-case synchronization between each iteration. Yet this too highlights the coverage advantage of Helix in that it can provide an overall greater speedup due to its better loop coverage. One of the key takeaways from our work is that non-numeric benchmarks have sufficiently complex loop structures that employ frequent loop carry dependencies both through registers and memory. In contrast, numeric benchmarks are more sensitive to static register loop carry dependencies than they are to dynamic memory dependencies. Their more regular structure means they benefit more from schemes like value prediction. Both types of benchmarks have loops containing frequent function calls, meaning stack parallelization is valuable to both. As both types of benchmarks exhibit frequent dependencies, the Helix-style approach for implementing pipeline parallelism has the best potential for achieving high speedups through maximizing coverage. However, the numeric benchmarks can do quite well with partial dual if stack parallelization and value prediction are also available. In conclusion, we find that existing loop structures, even in non-numeric codes, have substantial potential for extracting thread-level parallelism. Thus, a carefully designed speculative multithreading system that takes into account our analysis can still hope to continue sequential performance scaling. I'd like to thank you for your attention, and I look forward to discussing this work further and answering your questions at the conference.